Let's get into some trouble. Let's get into some trouble. Evaluate the series starting from k equals 1 to infinity of negative 1 raised to the k minus 1 over k multiplied by the infinite series from n starting at 0 to infinity of 1 over k times 2 to the n plus 1. To start, let's develop some tools with infinite series that you might be familiar with, starting with an infinite geometric series. An infinite geometric series will converge to 1 over 1 minus x when the absolute value of x is less than 1. So this is a very powerful tool in evaluating infinite series. So next, what we're going to do is we're going to apply a little calculus, that is integral calculus, to that infinite geometric series. Consider integrating that infinite geometric series with respect to x. The summation symbol and the integral symbol can be interchanged here, thus allowing us to take the antiderivative of x to the kth power, giving us x to the k plus 1 power over k plus 1 plus some constant. Right now that constant is arbitrary. Also, if we take the 1 over 1 minus x expression and integrate that, we get negative natural log of 1 minus x plus an arbitrary constant. So integrating both sides of the infinite geometric series equation shows us that we can compare this series to the natural log of 1 minus x, or the negative of that. To solve for that constant, we can bring the constants together on one side of the equation. Next, with a little bit of clever thought, we can use an x value, such as x equals 0, to find that constant. On the left-hand side, we get 0. And on the right-hand side, we get the negative natural log of 1, which is also 0. So c, the constant, is 0. That simplifies our expression. This infinite geometric series will become important later. If we make the substitution with x to negative x, we can actually change the nature of this expression. So on the left-hand side, plugging in negative x, and on the right-hand side, plugging in negative x, gives us something positive within the natural log, 1 plus x. On the left-hand side, we can re-index the series to bring it to k equals 1, and therefore we just adjust the variable k. Next, to get rid of that negative sign on the right-hand side of the natural log, we could think about perhaps dividing both sides by negative 1. That'll make the right-hand side positive. And the infinite series on the left-hand side will absorb that negative 1 by adjusting the coefficient of, the exponent of negative 1 here to k minus 1. So now we have a nice little tool here to use to help us evaluate this series. We're going to have to dive a little bit deeper here to get to the root of the answer here. So this series, let's rewrite this out again here. We have the summation from k equals 1 to infinity of negative 1 to the k minus 1 power over k, multiplied by that infinite series with n starting at 0 of 1 over k 2 to the n plus 1 power. Alright, so we have two things to notice here. Maybe we'll start with one. Notice the following is true. This part of the expression can be represented with an integral from 0 to 1 of x to the k 2n power, 2 to the n power, And since this is the same thing, we can just make a substitution into the series here. So taking a look, we'll rewrite this series. The first part of it is the same. And the second series there will now replace with this integral. Once that substitution is made, we can then rearrange a few things, and that's sort of the point of using the integral here, is that we can now rearrange the summation and the integral symbols, and that gives us the integral from 0 to 1 of the summation, the double summation of -1 to the k minus 1 power over k times x to the k2 to the nth power. And of course you can rearrange the summation order. And so we bring everything we want to focus on in the inside of that integrand, and that should look familiar. Check out rule number 2 up there that we just developed earlier. Those look very similar, and in fact we can make that rule similar if we make the substitution from x to the 2n. 2 to the n. X to the 2 to the nth power. Right, so substituting that into the natural log, and then we can substitute that whole series as the natural log. Then we have one series to worry about, and that makes our series that we're trying to evaluate here a little bit simpler to work with. So now there, in the integrand of this integral, we have an infinite series starting from n equals 0 to infinity of the natural log of 1 plus x to the 2 raised to the nth power. And we know if we add up logarithms, that can also be written as the log of a product of things. This is a rule from high school algebra that tells you that when you're doing a log rule, that if you take the natural log of a plus natural log of b plus natural log all the way up to, say, natural log of z, that's the same thing as taking the natural log of the product of a times b times all the way up to z. So that's what we're going to do here, is we're going to write that in more compact notation. So just like the sigma notation is used for summations, a large pi symbol is used for a product, an infinite product notation here. So we're representing that 1 plus x to the 2 to the nth power will be multiplied with different factors here within the logarithm. So now let's just let this be some kind of number, capital N. All right, this infinite product. We can note that then raising both sides of that to the exponential e, we have then that e to that power is that infinite product there. So we sort of narrow down what the insides of that natural logarithm are going to do, and we're going to see if we can evaluate that. We're going to do this infinite product using a kth partial sum approximation. Now I really should say it's a kth partial product approximation, not a sum. That's an error right there. So we're going to do some approximations to what this product might look like. So if we start off with k equals 1, then you'll have, starting from n equals 0 to n equals 1, you'll have two factors that'll multiply together and give us a polynomial of degree 3. And a very nice looking polynomial at that. All the coefficients happen to be 1. If we let k equal 2, then we're going to have a total of 3 factors to look at. And we can take the last factor, the last results we had from the first one, and bring that into our second problem here. And when all is said and done, we're going to have a polynomial of degree 7, all the coefficients being 1. All right, let's just take another look at, maybe let's let k equals 3 and look at that infinite product, well, that partial product, I should say. And we're going to get the previous product multiplied by the next term in the product, which would be 1 plus x to the 8th. And putting that all together, we get a polynomial of 15th degree. So if we look at the k value and try to associate it to the degree of the polynomial, we can write this out as a pattern in terms of k. So this kth product will give us a polynomial that has a degree of 2 to the k plus 1 power minus 1. Okay, so now we can apply this idea of a limit, letting k go to infinity. And so we can write this as the limit, as k goes to infinity, of this expanded polynomial, or we could write it out in compact summation notation, since we're going up to the 2 to the k plus 1 minus 1 power on n. Alright, what happens when k goes to infinity? The top of that summation symbol will also go to infinity. So we get an infinite series, which is a familiar one. It's the infinite geometric series. And it converges provided that x absolute value is less than 1. Alright, so now putting this all together, this infinite product can be represented as 1 over 1 minus x. So now our number capital N is the natural log of this product, so it's the natural log of 1 over 1 minus x, which we can rewrite as negative natural log of 1 minus x. So the negative natural log of 1 minus x is the infinite series of natural log of 1 plus x to the 2 to the nth power. So now we have a simpler way of writing that infinite series. So now integrating that simpler integrand, do a little u substitution here. And so S works out to be, our series is the negative natural log of u times negative du, which we can just absorb those two negatives together. But switching the limits of integration brings us back with another negative. So S ultimately is about evaluating the negative integral of from 0 to 1 of the natural log of u du. And we're not going to do this by integration by parts. No. We're going to do this using symmetry and inverses. So imagine the natural log function, which looks like this, and the area under the curve that we're trying to integrate from 0 to 1 is the shaded area right there. Now the natural log has an inverse function, which is e to the x. And so that would be the same thing as what we would get if we reflect the natural log over the line y equals x. It's known as the line of symmetry. In fact, when you want to find the inverse of a function, switch x and y and solve for y. So e to the x is the reflection over this line, and it looks like this. And so when we reflect the area that we're interested in over this line, we notice that it makes a switch from going underneath the x-axis to above the x-axis. And so therefore, the area that we can compute a little bit easier is the area under the curve for e to the x, but we have to remind ourselves that that area is going to be the negative of the area we're really after. So the negative of that integral from negative infinity to 0 of e to the x is a much easier integral to calculate. And plugging in the negative infinity, quote unquote, here, we get 1 over e to the infinity, which really is going to go to 0. So this leaves us with negative 1. So S is going to be the negative of negative 1, which is just positive 1, and that's the answer. This was from Putnam, 2016, question B6. Let's now consider an alternative solution. So if we start off with the 1 over k 2 to the n power plus 1 term, one can notice that every integer, call it m, greater than or equal to 1, can be written uniquely in the following form. M is equal to alpha times 2 raised to the beta power plus 1, where alpha is some odd number and both alpha and beta are non-negative integers. So to show you that every or any integer can be written uniquely such as this, Let's do a couple of examples. Alright, so let's say we have m equals 1. A very obvious case would just be 0 times 2 to any power plus 1 would give us 1. How do we get 2 out of this linear combination? So we have alpha equal 1, beta equals 0, and 1 times 2 to the 0 plus 1 gives us 2. How would we make 3? 3 can be made by doing 1 times 2 to the first power plus 1. Let's choose a random number like 97. 97 can be written as 3 times 2 to the 5th power plus 1. So any integer can be written uniquely in this way. So if we look at the denominator of our fraction up there, k times 2 to the n plus 1, we see that it has the same form. So now we consider all values of m that are greater than 1 because since n starts at 0, that would indicate m equals something greater than 1. M is equal to k times 2 to the n plus 1, and also it's equal to alpha times 2 to the beta plus 1. So if we put these together, k can be represented as alpha times 2 raised to the beta minus n power. Now, we can draw some conclusions from this relationship. As we let n run through the values 0, 1, 2, etc., we will get specific k values. But k must also be an integer. When we're doing a summation like this, k is taken to be an integer. So if k is equal to alpha times 2 raised to the beta power for n equals 0, and k equals alpha times 2 to the beta minus 1 for n equals 1, and so on, when we get down to the n equals beta minus 1 term, we get our last even value of k, and then the very last value for n equals beta, we get a k value that's just equal to alpha, and alpha is assumed to be odd. So now let's put this together. We have all these even k values and one odd k value. So that note, again, when n is equal to b plus 1, b plus 2, etc., when we go larger than beta, then we get a k value that is no longer an integer. So for beta plus 1, we get a k value of alpha over 2, which is not an integer. So therefore, n is then restricted to the values n equals 0, 1, 2, all the way up to beta. That is, in order to keep k an integer value. So now if k is equal to alpha times 2 raised to the beta minus n power, for all the values of n, starting from 0 to beta minus 1, k is an even number, and therefore k minus 1 is an odd number. For n equals beta, k is an odd number, so k minus 1 is an even number. This plays a role in our expression with negative 1 raised to the k minus 1 power. When that power is odd, we get negative 1. When that power is even, we get positive 1. And we only get positive 1 for n equals beta case. So now we need to organize these ideas together. The expression negative 1 raised to the k minus 1 over k multiplied by 1 over k 2 to the n plus 1, we note that the integer m is alpha times 2 to the beta plus 1. So subtracting 1 gives us m minus 1 is equal to alpha times 2 to the beta. And we know that k is equal to alpha times 2 to the beta minus n. For all the n values from 0 to beta minus 1, we noted that the negative 1 raised to the k minus 1 power was always negative. So making some substitutions here, and for the n equals beta case, we also understood that the negative 1 to the k minus 1 power was always going to be a positive 1, and so we get a simpler expression, 1 over alpha m. Now if we try to sum up all these terms, what does it look like? our original expression, our original sum, the infinite series from k starting from 1 to infinity, and the infinite series from n starting from 0 to infinity, of negative 1 raised to the k minus 1 over k times 1 over k 2 to the n plus 1, we can rearrange this summation initially so that we can bring all the terms together in front of the summation symbols. We want to represent this summation all in terms of the integer m. So taking what we just did here and summing up those two parts, the parts that gave us the negative 1 on top and the part that gave us the positive 1 on top, right? The n equals beta case and then the n equals 0 to beta minus 1 cases. If we add all those cases up, what does it look like? Again, m is greater than 1, and we can pull out a 1 over alpha m to give us a better idea of how to deal with the remaining summation inside. Focusing on the 1 minus the sum from n equals 0 to beta minus 1 of 1 over 2 to the beta minus n power, we begin to construct the idea of a geometric series. So expanding out that sum, we get 1 over 2 to the beta 1 plus 1 over 2 to the beta minus 1, all the way down to 1 over 2 to the 1 power. So this would be a geometric series that is just missing its first term, 1, that looks something like this. Starting at 0 to beta of 1/2 raised to the nth power, but missing the first term, which is 1, so minus 1. So now substituting that in, 1 minus this series, minus 1, will give us 2 minus the infinite series from n starting to 0 to beta of 1/2 to the nth power. And this is a convergent geometric series. It's a finite geometric series given by the formula Sn is equal to its first term multiplied by 1 minus its common ratio to the n plus 1 power over 1 minus its common ratio. Common ratio here is going to be 1/2. So explicitly putting that into our formula here and rearranging some terms, simplifying the expression. We find the 2's cancel each other out, and then we just get 2 times 1/2 to the beta plus 1 power, which will simplify to 1/2 to the beta power, or 1 over 2 to the beta power. Now finally, our sum for an integer greater than 1 of 1 over alpha m multiplied by 1 minus that infinite series we started with from 0 to beta minus 1 of 1/2 to the beta minus n power can now be simplified down to 1 over 2 beta in that expression. So now the summation is a much simpler expression. And rearranging some terms in the denominator here, we can notice that alpha times 2 to the beta was really m minus 1. And therefore we can write this now summation all in terms of m. Much, much simpler. So now we just have to figure out what this summation yields. Doing a little partial fraction decomposition, we can split 1 over m minus 1 times m into the sum of two simpler fractions that have each their own denominator, one with an m minus 1 and one with an m. And finding out the coefficients here of those fractions, or the numerators of those fractions, I really should say, we get a equals 1 and b equals negative 1. So this expression can be written as 1 over m minus 1 minus 1 over m. So we're going to substitute that into our series for m greater than 1. And if you're familiar with certain series, this would be a telescopic series. So the series is said to telescope, and you'll see kind of what's going on here. The first term is 1 minus 1/2, the second term is 1/2 minus 1/3, 1/3 minus 1/4, and if we would start to adding up these terms, there's a lot of cancellation except for the number 1. So this series converges to 1. We've shown, alternatively, that the series is equal to 1.